Good morning or good afternoon, everyone, depending on where you are. I'm Chris Spinagle from the Warning Decision Training Division. I'd like to welcome you to today's Storm of the Month presentation. Today's presentation comes to you from the National Weather Service office in Sioux Falls, South Dakota, as well as from the Warning Decision Training Division right here in Norman, Oklahoma. Our presenters are Phil Schumacher, Barb Boustead, and Steve Corfidi, who will be presenting Diagnosing and Warning for Organized MCS and Derecho Damaging Winds.
Thank you, Chris. Thanks, everybody, for attending here. And I wanted to point out that this is a special series for the Storm of the Month webinars. We are doing 3 of these that are going to be led by WDTD folks and some of their subject matter experts. And a couple of these topics were by direct request from our Sioux community, and warning on damaging winds was high on that list, so we wanted to address that right off the top. In February, we will do a Storm of the Month webinar on the new iSPIDA warning workflow. That replaces the SRAD warning process that many of you learned in your RAC workshop. And in March, we will have a webinar on side lobe contamination. So please continue to join us here for the next couple months. But getting back to the winds here and our purpose for today, a bit of a bottom line up front. We have added a bunch of wind training to Walksevere for our FY24 course. This builds on some of the content we introduced in RAC. Enrollment actually opens today for the FY24 course. That's January 24th for people who are listening to the recording. We will have 2 new modules coming out to address derecho winds specifically, and then we will also be addressing winds in our West case this year. So if this is something that is an area you feel like you want to learn more about, we strongly recommend that either you enroll in Walksevere or that you pull from our seasonal readiness training and put these into your training plans for this year. In this webinar, we're going to highlight some of the new training that we are pulling together. So first, we're going to have Steve Corfidi speaking with us, and he's going to dig a little deeper into some of the background and theory of derechos. And then Phil Schumacher from Sioux Falls is going to apply this to diagnosis and warning strategies in a complex wind scenario, and one that occurs with perhaps some frequency in derecho events and might require a bit of a paradigm shift for warning strategies. Isn't that a fun teaser? So with that, I'm going to go over to Steve Corfidi. Many of you recognize his name from his time at SPC or perhaps the vectors that are named for him. But we in WDTD know him as one of the members of our team. And he is an author of numerous papers on organized convective complexes, and he's got the floor now to share some of his deep knowledge about organized convectively induced winds and derechos in particular. Steve, go ahead.
Okay, thank you, Barb, and good afternoon or good morning to all of you out there. Given that time's a bit limited, we won't be discussing the mechanisms responsible for the development of strong convective winds, but as Barb suggested, we'll be focusing mostly on the most prominent form of organized convective windstorms, that is the derecho. So what is a derecho? Well, in basic terms, a derecho is a widespread, long-lived windstorm associated with a band of rapidly moving showers or thunderstorms. Note that the term derecho refers to the windstorm and not the convective system responsible for it. The term was first coined by Iowa State climatologist Gustavus Heinrich back in 1888. That's the phenomenon certainly not new to meteorologists, although it did go into a hiatus for about 100 years. Downbursts, concentrated convectively induced downdrafts, are responsible for the most damage and most intense damage associated with derechos. Those downbursts occur in clusters that are produced by bow echoes. Bow echoes, in turn, often contain a pair of embedded circulations known as bookend vortices, as shown in the schematic above. The strongest and most sustained winds typically occur with rear inflow jets that arise between the centers of these vortices. Next slide. While, of course, no official definition of a derecho exists, the AMS glossary and the SPC further distinguish the term derecho using both size and meteorological criteria. 1, a widespread convectively induced straight-line windstorm, specifically a family of particularly damaging downbursts produced by a mesoscale convective system. 2, and this is important, derecho-producing MCSs have sustained bow echoes with bookend vortices and or rear inflow jets that produce damaging straight-line, that is, non-tornadic winds. So we're trying to get a meteorological component to the definition. The damage occurs continuously or intermittently over a swath of at least 650 kilometers or about 400 miles long and 100 kilometers or 60 miles wide. Finally, although not part of the current AMS SPC definition, an important characteristic of derecho storms, and one that's going to be addressed by Phil in the latter part of this talk, is the prolonged nature of the damaging winds. Although high winds often accompany the associated convective system's gust front, a key characteristic of many derechos is the onset or persistence of high winds tens of minutes to sometimes an hour after the system gust front is passed. Two main classes of derechos are generally recognized: progressive and serial. The two categories are based on the primary physical processes responsible for their development. Progressive derechos are associated with expansive regions of very moist, unstable air and typically evolve from a single bow echo or storm cluster that grows into a forward propagating MCS as new cell development occurs rapidly and sequentially in the downshear direction. The associated derecho producing MCS is oriented perpendicular to the upper level flow and moves faster than the flow. That's an important characteristic of progressive derechos. Progressive derechos are primarily warm season, occurring from late spring through summer, and they can yield high winds that sometimes persist, as I mentioned, for up to an hour after the system gust front has passed. Serial derechos, in contrast, are associated with strong, fast-moving upper-level troughs and surface low-pressure systems. Serial derechos consist of a series of bow echoes, hence the name, that are embedded into an extensive squall line along or ahead of a cold front. The bow echoes typically move roughly parallel to the cloud layer flow and tend to move more slowly than that flow. Serial derechos are primarily cool season phenomena and on occasion affect swaths up to 1,000 miles in length. So what are the primary meteorological characteristics of derecho producing environments? Basically, one with an expansive warm sector, meso-alpha scale perhaps in nature, all the way up to 2,000 kilometers in extent, having the following characteristics. First, seasonably rich low-level moisture. That is for progressive derechos, surface dew points averaging above 70 degrees Fahrenheit, and for serial derechos, at least into the mid-60s Fahrenheit. Second, steep low to mid-level lapse rates, with the latter, the mid-level lapse rates, typically associated with an elevated mix layer. And the role of that elevated mix layer is to inhibit or limit the extent of deep convective development outside the derecho producing MCS. Third, seasonably strong and unidirectional surface to 500 millibar shear, with magnitudes greater than 30 knots for progressive systems or greater than 50 knots for serial systems. And it's worth noting that faster flow above 500 millibars, that is stronger deep layer shear, is important in enhancing the potential for derecho development. And finally, a sustained focus for ascent. This could be take the form of a weak stationary front oriented parallel to the upper level flow, a lee surface trough, or a weak lower tropospheric warm advection pattern in the case of progressive systems, which recall are typically warm season phenomena, or in the case of serial derechos, strong cold front and associated surface fronts that have concentrated convergence. Derechos are difficult to forecast, not that we need to tell you here, because their development depends on storm scale processes that are not well resolved in the operational model fields and certainly not in the observational fields. Nevertheless, forecast confidence can be increased when the following ingredients appear in the, say, day 1 to day 3 data. First, a wide, seasonably warm and very moist capped warm sector lying beneath relatively fast and largely unidirectional mid to upper level flow. 2, sustained synoptic or mesoscale ascent. The mechanism can be, again, a locally enhanced warm air advection pattern that we already mentioned, or upper level divergence zone associated with a passing upper level jet stream to initiate the first storms in a relatively confined or mesobeta scale region. Third, modest but persistent downstream directed lifting. This often is due to the same weak localized warm air advection that helped initiate the first storms to foster downstream convective development. And finally, favorably timed onset of daytime heating and low-level destabilization in the region downstream from the storm initiation zone. This favors downstream propagation or forward propagation. Once these ingredients are in place, the greatest high wind threat should focus along the downwind edge of the expected elongated cold pool, that is, in the downstream downshear direction. Any flash flood threat would most likely occur on the equatorward side of the elongated cold pool associated with the developing convective system. And this, of course, would occur after upscale development into a derecho-producing MCS has occurred. The development of a typical progressive type derecho is depicted schematically here in these illustrations. First, the initial storms form in a region where strong, nearly unidirectional mid to upper level tropospheric flow, here assumed to be westerly, overlies a broad area of high potential instability, especially in an environment with rich low-level moisture and steep low to mid-level lapse rates that together yield very high CAPE. Uplift along the composite gust front from the initial storms sequentially spawns new storm development in the downstream direction as the associated cool air dome preferentially elongates in the direction of the mean flow. And that's the importance of the unidirectional flow. It causes the cold pool to elongate preferentially in one direction and can act as a snowplow of sorts to cause that downstream or downshear propagation. And that's what we call forward propagation. Third, rapid downstream directed convective development results in anvil cloud material being left behind in the wake of that progressive gust front. This is what fosters the formation of the evaporatively induced rear inflow jet that was mentioned earlier that enhances the front to rear flow at mid-levels into the backside of the convective system. And it is this flow that is sometimes enhanced by the presence of those paired rotating storms, the bookend vortices, on either end of the bow echoes that furthers the development of new storms along the system gust front, and again, furthers the forward propagation component of these convective systems. New cell development and the potential sustenance of derecho strength winds is perpetuated as long as the thermodynamic and kinematic fields remain favorable for deep convection in the downstream direction. So the length times of the derecho-producing convective system is a function of how moist and unstable and favorable the shear environment is in that warm sector extending downstream from the initiation zone. Finally, embedded supercells and smaller scale circulations can locally augment outflow winds and yield corridors of enhanced derecho damage. And speaking of those circulations, although storm downdrafts produce most of non-tornadic derecho winds, observations and numerical simulations definitely indicate that the most prolonged extreme winds and the significant damage associated with those prolonged winds occur in association with embedded circulations known as mesovortices. Derecho mesovortices can range in size from the mesogamma to mesobeta scale, say roughly 20 to 200 kilometers in size, all the way up to and occasionally to the meso-alpha scale on the order of 1,000 kilometers in size. Mesovortices can form in several ways. The development of a rear inflow jet and the strengthening MCS can yield a pair of counter-rotating mesogamma to small mesobeta scale bookend vortices, as we've talked about, astride the jet. These are shown in red in the top schematic. Dynamically enhanced updrafts in these rotation centers can then further strengthen the MCS. Downward bending horizontal vorticity by storm downdrafts can yield a pair of counter-rotating vortices on the horizontal vortex tube that marks the leading edge of the MCS gust front. That's shown in green in the schematic, the middle schematic. Vertical stretching of the vortices by, for example, the chance superpositioning of an updraft over one of those vortex pairs can then yield short-lived tornado strength circulations on tornado or derecho gust fronts. Horizontal shear instability is another source of smaller scale circulations, maybe on the order of a mile or two in diameter along derecho gust fronts, when the background wind shear and buoyancy are great. These vortices may sufficiently strengthen to produce tornado-like damage as well. And finally, mesovortices within a derecho-producing convective system can arise from the ingestion of existing discrete supercells during the earlier stages of derecho-producing convective systems development. And these residual embedded supercells and their associated mesocirculations can actually persist for hours. And in the corresponding panels there, pair of velocity and reflectivity, you can see the number 3 as a vortice there. It was a result of an ingested supercell long before those two panels were made. Okay, Barb, that's all I have here. I'll send it back to you.
Thank you so much, Steve. I appreciate your expertise here, and Steve will be hanging on through the end for questions. So if you have questions and want to mine his deep knowledge, hang on and get ready to ask those. But now we are going to switch over to Phil Schumacher, who is currently the SU at WFO Sioux Falls. And Phil is going to highlight some best practices for diagnosis and for warnings using a fairly recent Derecho event in the Sioux Falls area. And Phil, it is now on you.
Okay, thank you, Barb. So we're going to start off right off with a question from for Poll Everywhere. So let's go to the next slide. And what I want you to do here in just the next few seconds is, where do you think the strongest winds will be in the next 10 to 15 minutes associated with this derecho? This derecho is actually fairly mature at this point. It started in north central South Dakota in the late morning. It's now mid-afternoon. So would you think it would be at point A, which is the apex of the QLCS, point B, which is actually, it's hard to tell here, but it's actually in the RFD of the embedded supercell, point C, which is on the south of the apex of the bow, or point D, south of the cyclonic bookend vortex. So we'll just give you a few seconds here to answer, and we'll see what we get. So let's go ahead. We'll see the responses here. And so most of you said the RFD and the embedded supercell, which from what Steve said is a very good place to look. But in actuality, it's actually point D. It's south of the cyclonic bookend vortex in this case, and in several other cases with mature derechos that have a strong cyclonic bookend vortex and rear inflow jet. In this case, at A and B, winds were generally right around 50 to 55 knots. At point D, they were sitting between 65 and 75 knots at this point of time, and that continued for quite a while in these areas, as you'll see in a little bit. So it's a lot different. I would have answered, before this case, I would have answered exactly the same as all of you. So we went back and did an after-action review with our office and looked at this case after we saw that the strongest winds were at point D and not where we expected them at point A and B. So if we go to the next slide, I just kind of want to talk about, again, going back to what Steve said, but I'm going to focus a little bit more on the development of those winds, those persistent long-lived winds that result in the very strong, in many cases, destructive wind gusts that can occur in the south of the cyclonic bookend vortex. So as Steve mentioned, a lot of times bow echoes will start off as multi-cells along a weak boundary or a supercell with a strong RFD that expands out. Usually some sort of HP supercell, and you end up with a line, and most of those cases you end up with the strongest winds along the gust front as this developing bow echo forms. As we go to the next slide, you can see that as it forms, you continue to grow the cells downward, the line QLCS downward, the derecho, and as that happens, as Steve showed, you get the development of a rear inflow jet, and as that rear inflow jet develops, you get the development of a cyclonic bookend vortex. You also, as you mentioned, get an anticyclonic bookend vortex, but we're going to focus only on the cyclonic side of this for this case. And so one thing Seth Banal, who's been helping me a lot with this, and I have noticed, is that in several cases, instead of the wind staying confined to the gust front, such as here, you'll actually see this large area of very strong winds that develop between the cyclonic bookend vortex and the rear inflow jet. And it's possible it may be tied to having precipitation in that area that allows for evaporative cooling and downward transport of that high momentum air to the surface. Although that really needs to be looked at a little bit more. But it's this area that can become a real quandary, this area south of the cyclonic bookend vortex, that can be an area of intense damage, but also a quandary from what to do from a warning perspective. So if we go to the next slide, we'll just see a few examples here. And this is from different areas across the country. First off, we'll start off from just Labor Day, past Labor Day. Chauncey Schultz showed me this case and mentioned it to us. Oops, sorry. And what we found here is in Bismarck, we had this bow echo developing derecho move out of South Dakota into the Bismarck area. And when the outflow boundary went through, which is highlighted in blue here, he had winds gust up to about 55 miles an hour. So not even severe at that point. And you see this in all these cases, the winds drop off as that gust front goes by, which is what we're used to seeing with gust fronts. You get this rush of wind and then a gradual decrease over the next 15 to 30 minutes. And they're well sub-severe by the time you get about 40 minutes after the gust front went through. And then about 45 to 50 minutes, you see the winds begin to pick up again. So cyclonic bookend vortex moves nearby. You see the winds actually pick up and are actually stronger than what we had along the gust front. They picked up to 65 miles an hour. And notice that the winds stay above 50 miles an hour for about 15 to 20 minutes here in the Bismarck area, over an hour after the initial gust front went through. It's something that we're not used to either messaging, nor are we used to seeing. And just one point is that when Seth and I have looked at these, as well as in our office here, this is not a wake load that's developed. There is not a rapid pressure fall that you typically see with a wake load, nor do you see the divergent pattern with this. This is actually still, in this case, southwesterly winds associated with this complex. So it's actually part of the convective system per se. So if we go to the next slide, you see another example here. This is from the super derecho that went through southeastern Kansas, southwestern Missouri. We're looking at Joplin, which is right here, and this has an extremely large cyclonic bookend vortex. But we see the same signature in Joplin. You see the gust front go through, winds pick up, in this case, gust over 70 miles an hour, but they rapidly drop off after the gust front goes through. We drop with gusts below 50 miles an hour for about 10 or 15 minutes. And then they really pick up again as that bookend vortex gets closer. We see a gust up to 85 miles an hour. Now, in this case, we don't have the high-resolution data that we currently get with the 5-minute data that you can get off of MesoWest. But you can see that winds were above 60 miles an hour for at least 20 minutes at Joplin. And this occurred again almost an hour after the gust front went through. If we go to the last example we have, this is from Beaver Creek. This is from July 5th. This is Beaver Creek, Minnesota. And what I want to do is kind of talk about how I'll say how our office approached this as we went through this event. And we have a lot of our WIS stations in South Dakota and Minnesota, and our practices is we'll monitor those stations. So we'll go through, monitor it, look for a case where the winds pick up with the gust front. We're looking at radar, and then we start looking for when the winds drop off. As you see here, they start dropping off, the gusts drop below 40, and then we'll go on to the next station downstream and start looking for the same thing. That's the way we monitor it. But as you can see here, had we continued to monitor the winds in this case, you see the winds did drop off, but then they pick right back up, and they peak an hour after the gust front came through at over 80 miles an hour when we're right between the rear inflow jet and the cyclonic bookend vortex. And more importantly, notice that you're up above 55 miles an hour from basically 1630 to 1730. So for almost 1 hour at Beaver Creek, you had severe wind gusts going in that area. And that occurred here at Sioux Falls as well. And you could actually, it looked like probably the closest I'll ever see to a hurricane in the central U.S. with, the rain blowing basically sideways. It was pretty surreal, not something we usually get around here. But notice what I want to point out is the long duration of these winds and the fact that there is a lull in between. And that becomes very important, as we'll talk about later, in terms of messaging this to both the media, our partners, and the public. So if we go to the next slide, we're going to start with another question here, and just 3 answers this time. But we want you to think about what's the best warning strategy to cover the hazards for this event. And so not only have I drawn polygons here, and if you're wondering why B is as an odd-shaped polygon, it's because that's the CWA line. In this case, Omaha would obviously have another warning to our south. But I also include the path cast and the severe tags on here, hail and wind. And so there's hail embedded in here because we have an embedded supercell, but you can see the different winds. So go through here and just pick on here which of these 3 polygon configurations you would use if you were issuing warnings for this event. I'll give you a few seconds again. Okay, yeah, that's really good. Everybody picked, the majority picked C, which is something that we have evolved to as well here in our office. On this day, because we didn't have the paradigm for how this could actually develop, we actually had done B. And when I say we, I mean myself. I was the warning operator at this point. And when we found out there were strong winds behind it, we went with B. But then after the fact, as I said, we did an after-action review. And one of our forecasters, Samantha Garrett, actually went through it and proposed doing what all of you selected, which is C. And that's what I'm going to go through here in a second. And we're going to switch here. I'm actually going to show you why I also said you would not want to necessarily use a pathcast for warning C here in an example. So Barb, if you want to give me screen control, I'll go on West in the Cloud here and we'll just quickly look at an example of warning with this system. So hopefully everybody can see my screen here. And so what we've got is in blue is the downstream warning. So that's that first warning, and that's essentially for the gust front. So you issue your first warning for the gust front. We have 60 miles an hour. That, for those who may care, it's for the city of Sioux Falls at this point. And you notice that goes back to the high reflectivity core back in the line. So it's mainly to handle that first surge of winds that we showed earlier. So what I've got here is now the second warning, the warning for the prolonged period of winds that we have here. And so the first thing I'm going to do is, first thing I'm going to hit is play. And then I'm going to do create text. And for this first example here, I'm going to actually use the full pathcast. So if I hit create text here, hit enter, and hopefully I did keep under 12 counties. I counted that. I'm not going to fill in the destructive storm. We did have reported 80+ mile an hour gusts at this point. But what you need to look at is the pathcast here. So I understand you don't know RCWA very well, but I use this line right here, the back edge of the high reflectivity for finding my pathcast. And if you look at this pathcast a little bit, what you'll notice is that all these towns here are located out ahead of this line. And what does that, and with a specific time. And what does that mean? That means all these areas back behind this line here, one including Mitchell, South Dakota, have no time and they're not listed in the warning at all. So for a person who receives this warning, it may be very confusing, including the media and partners. It may be confusing because we're not mentioning, say, Mitchell or other towns back here that are currently experiencing 80+ mile an hour winds. So that's why what we propose doing is actually when we draw this or do this, instead of selecting pathcast, actually select a list of cities. So if I click on that here and hit enter, and I'll move this back over, you'd have to know a little bit about the area. But again, you start seeing more cities like Washington Springs. Washington Springs is back on the back edge of our polygon here. It never showed up when we had the pathcast on. Woonsocket is back here. That never showed up with the pathcast on. And so cities that are getting Mitchell, over 10,000 people back here, did not show up either. So you get all of the cities that are impacted. And one of the messages you want to send out, and we'll talk about that in a second, is this is a long duration event. This is not going to be 10 minutes of high winds and you can leave. This is 30, 40, 50, 1 hour. A few places here had over an hour of 55+ mile an hour winds. And by putting a time in there, you actually, you're giving a time that doesn't apply to a lot of places. You're missing places. And you may be implying that the storm is going to be relatively short-lived, like everybody's used to experiencing. So Barb, I'll give you back the control, and we'll go back to the talk. So this is kind of the warning strategy that we came up with in our office, and then talking to Barb and to Seth, we've kind of manipulated or massaged a little bit to come up with what we thought is the best strategy. So the first warning you issue will be, again, out ahead, associated with the gust front. So these winds are out with the gust front and out ahead. Try and draw it with where the strongest updrafts are located. And, you go 45 minutes or, put in the take that's appropriate based on the winds you're getting with the gust front at this point. So, in our case, it was 60 miles an hour. And this is found if you go through the advanced warning strategies module, they talk about this precise way of doing things. And notice I didn't do the whole line. I stopped near the apex, and then we would issue another warning south of there for if these storms were severe down here. But then when we get to our winds behind the line, if you go to the next slide, that's where our second warning is. And this is going to be a module that Seth and I are working on, talking about warning strategies and operations and talking about specifically why we want to issue this. But notice that what we do is we go back to the back edge of our strongest winds and go out ahead of it a little bit. In this case, I just went out to the gust front. As you saw in my prior example, it went out a little bit farther than that, depending upon the speed of the system. Generally, it will be fairly parallel to your rear inflow jet in that case. And again, you use locations, list of cities, not a path cast in this case, because of the long duration of the event. So if we go to the next slide, the last thing I want to talk about is communication, and this is really important. These are complex and rare situations. Your CWA may see this once in a decade, or maybe twice in a decade if you're in the Ohio Valley. And it really violates our expectations and the public's expectations of how these storms work. You need to be, everyone expects maybe 10 or 15 minutes of severe weather, whether it's large hail or damaging winds. We all know there's exceptions to that, but that's generally the expectation. And then once the winds stop or the hail ends, you can get out of your place of shelter and move on. But that's not the case in this case. In fact, the lull can lead people to think it's safe when it's not safe. And there have been times where people have actually gotten out of shelter after the first gust front went through, even gone outside, and then the next gust of winds have hit, which are even stronger than the first gust of wind. So we don't want people getting out. And so it requires you to be constantly monitoring your observations, but it also needs, we have to talk to our partners. So a bright way is through Slack. Tell the media especially, but also your partners, that why you issued that second warning. You put it out there because winds are going to last for 30, 40, 60 minutes, and it's going to be stronger than what we saw before. And we need all our partners echoing that message, whether it's the EM community or the TV media, which a lot more people meet. So going into Slack and describing this to them, explaining it to them is really important. The idea is you stay in your shelter because winds are going to pick back up again. And for Sioux Falls in this case, that was really important because the winds came through right during the evening rush hour. And so you can imagine if we had lots of people on the road, which we probably still did, that could have been a disaster had winds picked up to 100 instead of only, we picked out at 80 here. So if we go to the last slide, the other thing you can do with communicating is talking to people through social media. And to really hit on certain keywords, like you're not talking about one area, you're talking about this whole entire area receiving 70-mile-an-hour winds, and you're talking about 80 plus within this oval, and highlighting the idea that it's going to be up to an hour. So it's not just a short duration event, that's going to last a long time, and so people have to prepare to stay in shelter and an increased likelihood of loss of power in these type of events. So these type of developing some templates for social media, even ones you could share with the media on Slack, could be really important to amplifying that message and getting it out there. So that's all I got. I will pass it back to you, Barb.
Thank you, Phil. And just a few bullets here to recap as a summary. You can anticipate derecho formation via the environment, although some of the cues are pretty small scale and may not really show their faces until the situation is evolving. And you can interrogate the structure of a line for cues to enhanced wind damage areas, and these include the diagnosing where the rear inflow jet is, as well as that area between the rear inflow jet and the cyclonic bookend vortex, which seems to be a channel for enhanced winds. And then finally, of course, interrogating for mesovortices, where even if you don't get a tornado to develop, you can get enhanced damaging winds where those mesovortices occur. And then to warn using the best practices and the strategies that we present in our training. And these are supported by science, they're supported by directives, and they're supported by best practices that come in through the field to WDTD, where we can vet them and have, you know, a whole committee looking at these recommendations. And that's exactly how we have evolved this process for both the advanced warning methodology for wind module and the new one on derechos that Seth and Phil are developing. So I'll remind you all, of course, being a training person, to refer to Walk Severe and the associated seasonal readiness training for that fresh training on derechos. And And finally, just leave this here as we go into questions. Thank you so much for joining us. And thanks to Steve and Phil for sharing their expertise. They are here to answer their questions along with myself and a couple of others from WDTD. And I've also left Steve's email address here, and I didn't put Phil's on here because I don't think it's going to work a whole lot longer, but I am hoping you all can give your questions here, and for those who listen to the recorded version, you can email those questions to the RAC Help email address and any or all of the presenters here.